Uh, we also, before I get to this slide, there was a mathematician named Paul Erdos. He had a lot of influence on Terence Tao. Um, he announced that he would award $10,000 to the person responsible for solving his prime gaps conjecture about how large they can get. He said that it should be possible to replace the one-third in Rankin's equation by a larger number, so the prime gap could be larger than in Rankin's equation and smaller than in Cramer's. Um, okay, so now on to the next slide. Sorry for jumping ahead. In 1937 and 1964, Kramer and Shanks, respectively, conjectured that P of n is similar to e to the square root of n. And then Wolf conjectured, to better agree with numerical evidence, he conjectured that P of n is similar to the square root of n times the e to the square root of n. So, and then he also conjectured, this is Wolf, that the maximal prime gap between integers less than n appears around g of n similar to n over the prime counting function of n times the quantity of 2 times the natural logarithm of the prime counting function minus the natural logarithm of n plus the natural logarithm of 2 times the twin primes constant. And this is all equivalent to small g of n. For large n, setting the prime counting function to similar to n over the natural log of n reduces to Kramer's conjecture and leads to g of n similar to the natural log of n squared. The Hardy-Littlewood conjecture states that there are infinitely many n in the positive integers such that every element of the tuple n plus h1, n plus h2, etc. to h or n plus h sub k, where h sub I is a specific integer shift, is prime. Sorry about that. So that's what I just said in the first bullet. Another mathematician named Gallagher showed that if the Hardy-Littlewood conjecture was true, then the prime gaps p sub n plus 1 minus p sub n with n less than or equal to x were asymptotically distributed according to an exponential distribution of mean of log of x, in the sense that this big equation that takes up most of your screen is equal as x goes to infinity for any fixed lambda greater than or equal to 0. This equation I'm going to call Hardy-Littlewood conjecture equation. And also, extrapolating this equation to the regime lambda and log of x leads you to Kramer's conjecture, because the quantity of e to the negative lambda plus O of 1 times x over log of x is less than 1 when lambda is sufficiently larger than log of x. But the equation only uses fixed lambda, so Gallagher could only establish the weaker bound g sub p of x over log of x as it goes to infinity. Okay, and then we jump up to 2005, where we get these three. Dan Goldson, Janos Pintz, and Sem something proved that there are infinitely many prime numbers such that the distance to the next prime number can be as small as we would prefer when comparing it to the mean distance between consecutive prime numbers. So here they apply the Selberg sieve, which removes the tuples where there exists at least one component that has a small prime factor. This only leaves tuples where the prime factors for all components are large. Thus, the remaining tuples have less prime factors among their components, As a result, we obtain a sequence where it is more common to find prime numbers with smaller prime gaps. The level of distribution of primes in arithmetic progressions is used to detect the primes in the tuple. Okay, and about 8 years later, in 2013, Yatang Zhang, on April 13th, announced a proof that no prime gap is any greater than 70 million. This is one of the biggest breakthroughs in prime gaps in the great amount of years. So this also proves that the prime gaps is bounded. Applying the findings of Goldston, Pintz, and Yildirim, Zhang shows that in the Selberg sieve, he can limit the sieving to divisors with 0 large prime factors. This decreases effectiveness of the sieve, but he shows that this decrease surprisingly has a relatively small effect on the method. Next, he increases the sieving range corresponding to a level of distribution 1/2 plus 1 over 584. This turns out to be great enough for him to make up for the loss from removing the large prime factors and shows bound gaps between primes, provided that all of the error terms can be controlled. The divisors in the sieving must not have any large prime factors, and consequently, they may be factored into factors of various sizes with considerable flexibility. As a result, all of the error terms are controlled. However, this does not allow proof that the primes have a level of distribution greater than 1/2 in accordance with the definition of the level of distribution. Zhang proves that every k tuple without the restriction that some prime number always divides one of its components, or admissible k tuple with k equals 3,500,000 contains 2 primes. All right, jump ahead 6 years. We get to 2019, where William Banks, Kevin Ford, and Terence Tao published their paper Large Prime Gaps and Probabilistic Models on August 22nd. This introduces a new probabilistic model of the primes consisting of integers that survive the sieving process when a random residue class is selected for every prime modulus below a specific bound. This paper provides an understanding between the connection between the Cramer conjecture and the Hardy-Littlewood conjecture, which I have reiterated here on the slide. So, as you can see, in the Cramer conjecture, if x is a large number, then the largest prime gap, g sub p of x, is yada 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 yada. Okay? Now we go back to Gallagher's equation, which is that big old thing up there. Banks, Ford, and Tao wanted to configure the parameter choices lambda to grow with x, inputting a stronger version of the Hardy-Littlewood conjecture in which the length of the k tuple h equals h sub 1, all the way up to h sub k, and the magnitudes of the integer shifts, which would also grow with x. Tao says our initial objective in this project was then to quantify exactly what strengthening of the Hardy-Littlewood conjecture would be needed to rigorously imply Cramer's conjecture. So then they formed a theorem from their results. From here, the 3 authors can recover Cramer's conjecture given a sufficiently powerful version of the Hardy-Littlewood conjecture on the average. Okay. Now we come back to Harold Cramer. He made a random model C of primes in that every natural number greater than or equal to 3 is selected for membership in C with an independent probability of 1 over log of n. He also showed that the largest gap, capital G sub capital C of x, is almost certainly similar to the quantity of the log of x squared. but it does not obey the Hardy-Littlewood conjecture. Rather, it is a condensed version of the conjecture where the singular series is absent. Then Granville steps in, and he poses a refinement where he sieves out in each dyadic interval x to 2x all residue classes 0 mod p for p less than or equal to a. For a certain threshold, a equals the quantity of the log of x to the 1 minus O of 1 equals O of log of x. And then places each remaining natural number n in his set with an independent probability of 1 over log of n times the product of 1 minus 1 over p for to the negative 1 for p less than or equal to a. Continuing with this refinement, he then showed that the largest gap in this model was almost certainly greater than and roughly equal to spirally snake symbol times the quantity of the log of x squared, leading to his conjecture that this bound was also true for the primes. Yet, due to the need to shorten the singular series at the logarithmic cutoff a, it does not provide a reduction in the error term of the Hardy-Littlewood conjectures. All right. Now, from this, Banks and Ford and Tao, they experimented until they produced a manageable yet somewhat more complicated random model R, not to be confused with the set of all real numbers, which is a different R, for the prime numbers which complied with the Hardy-Littlewood conjectures with power savings. It also reproduced Granville's gap prediction of greater than or equal to spirally snake symbol times the quantity of log of x squared, as well as an upper bound of roughly about spirally snake symbol of log of x squared times log of x over 2 times log of x for both models. This model, the model involves non-trivial coupling between the events n elements of R as n varies, although the moment methods are still feasible and allow you to confirm the Hardy-Littlewood conjecture by straightforward calculation. The three authors selected one residue class, A sub p, where mod p, where p is less than or equal to z, and described their model as so, with that little bullet point right there, where z of t is Polya's magic cutoff, or the cutoff that gives R a density consistent with the prime number theorem or the Riemann hypothesis. They then state the upper and lower bounds and show that the Hardy-Littlewood conjectures hold with power savings for k up to the quantity of log of x to the c power for any fixed c less than 1, and for ships h1 to h sub k of size capital O of the quantity of log of x to the c. However, this is weaker than what their theorem requires because of the endpoint c equals 1. The three also proved a more precise, almost sure asymptotic formula that involves the optimal bounds for the linear sieve or the internal sieve, in which one deletes one residue class modulo p from an interval 0 to y for all the primes p up to a given threshold. The lower bound in their theorem relates the case of deleting the 0 mod p residue classes from the closed interval 0 to y. The upper bound comes from the delicate analysis of the linear sieve by Iwaniec. So this pretty much concludes all there is on prime gaps as of late. In the future, we are likely to see a lot more developing, given what we have now. But for now, that is all I have. Thank you for listening, and hope you have a good night.